A/B tests are slow and risky when two rankers are close. Interleaving lets you compare them on live traffic in Python and see which ranking actually wins sooner. This is the pattern you'll be able to implement by the end, which interleaves two rankers on live queries and decides the winner from clicks. I'm Professor Pi, teaching search and IR with simple Python. Search teams often face a tight race between two rankers. Classic A/B testing needs split traffic and many sessions to reach a confident decision. That costs time and can expose users to a worse ranking for weeks. Interleaving solves this by mixing two candidate lists into a single slate per query. Users see one coherent list, and their clicks are attributed back to each ranker. So you get comparative signal faster and with less exposure risk. Imagine two simple rankers that disagree on the top 3 results for a query. Interleaving will merge their picks into a fair combined slate. If clicks favor one ranker across sessions, you know which ordering better matches user intent. This trains a little implementation complexity for much faster decisions. It works well at the scale of live queries where you can afford per query merging and short click simulations. We will build a tiny, repeatable example in Python so you can feel the mechanics. The goal is not production-ready code, but a clean pattern you can drop into a service. I'll keep the corpus the same across steps so you can follow each change and see how decisions evolve. Now we'll build the tiny corpus and baseline ranker. This snippet builds a tiny interpretable corpus and a minimal lexical ranker A to produce a top 3 list. The variable docs maps short document IDs to simple texts. The function rankA scores each document by counting unique query term matches from the variable Q, which is split once and stored as the set QT for efficient membership checks. The dictionary S holds per document scores, and sorted selects the best K documents by score, breaking ties deterministically by Python's key ordering. The resulting list A top shows the shallow ranking for the query. The printed ranking confirms the baseline's preferences and provides a stable reference for later comparison. Next, we will create a competing ranker that favors different signal patterns and measure how much they disagree. This example defines ranker B using a simple semantic leaning heuristic that favors the terms late and dense to mimic modern interaction and dense retrieval signals. The variable S stores scores that give a heavier weight to late and a lighter weight to dense. Then sorted returns the top K documents. To quantify ranking disagreement, the code builds position maps, PA and PB, for the lists A top and B top. The variable FR computes the Spearman footrule distance over the shared top 3, summing absolute position differences per document. Larger values indicate greater ordering divergence. The printed list and distance reveal B's reshuffling relative to A, which matters for interleaving. Now we'll implement the team draft interleaving to build a merge slate and keep track of ownership. This code creates a team draft interleaving function that merges two rankings while attributing each place document to its source team. The parameter A first toggles which team selects first. Turn flips each placement to alternate picks. The set used prevents duplicates by skipping already placed documents. And the tuple owner doc ID in out preserves both order and ownership needed for unbiased credit assignment. The while loop stops at K placements to ensure a fixed depth slate. Increasing K adds depth and more mixed exposure, while decreasing K concentrates credit on head positions. The printed slate shows the visible merged list and who owns each position. Next, we'll simulate a single user session, clicking on that interleaved slate, and assign credit back to teams. This snippet simulates one user session's clicks on the interleaved slate and assigns credit to the owning team. The function simulate clicks accepts the slate and a relevance map rel with small integer gains. The list base encodes a simple position bias, and the click probability multiplies that bias by a relevance scaled factor, yielding a Bernoulli draw per position. The variable credit accumulates team credit by summing clicks for each owner, while out records which documents were clicked. Raising the top bias increases head click dominance. Increasing the relevance weights amplifies content differences across teams. The printed credit clarifies which team benefited from the observed clicks for this session. Finally, we'll run many sessions, alternate first picks to balance bias, and compute a basic significance estimate. This example runs multiple interleave sessions, alternates who starts to balance first pick advantage, and reports a simple significance estimate. The loop builds a slate using interleave, simulates clicks with simulate clicks, and counts which team wins the session by total credit. The variables WA and WB tally wins, ignoring ties to match a sign test style comparison. After the loop, the code computes a two-sided normal approximation p-value around a null win rate of 0.5 using the error function for the Gaussian CDF. More sessions reduce variance. Fewer sessions react faster, but with wider uncertainty. The printed win counts and p-value indicate whether one ranker is credibly better under interleaving. To map this toy to a real system, swap the tiny corpus for a real document store and replace the simple click model with empirical click-through rates or logged position bias estimates. Run interleaving in a low-latency service that merges two candidate lists per query and logs owner credit on real clicks. Aggregate wins across query segments that matter, and use the same alternating starter to avoid systematic first pick bias. Recap: interleaving merges two ranker lists into a single slate and attributes clicks back to each ranker. Use it when you need faster, lower risk live comparisons than full A/B tests. One caveat: click models and position bias matter. Incorrect bias assumptions can skew credit. Next step: tune the position bias parameter in the click model to match your actual user click decay, and observe how the winner changes. If short, practical IR helps, subscribe and watch the IR videos.